Hello, in today's tutorial we're going to look at this question involving proof by mathematical induction. It has to do with a formula for derivative of a function. The question says prove by induction that for n belonging to the set of positive integers, for y equals ln of 2 plus 3x where x is greater than negative 2/3, d to the ny over dx to the n equals negative 1 to the n plus 1 n minus 1 factorial times 3 to the n all over 2 plus 3x to the power n. To do the proof, we're going to start with the base case, the case where we have n being the first positive integer, n equals 1. We have that d to the 1 of y all over dx to the 1 equals negative 1 to the 1 plus 1 into 1 minus 1 factorial 3 to the 1 all over 2 plus 3x to the power 1, and that gives us negative 1 to the second into 0 factorial into 3 to the 1 is 3 all over 2 plus 3x to the 1, which is simply 2 plus 3x. So finally that first derivative would be negative 1 squared is 1, 0 factorial is 1, so 1 times 3 would just be 3 all over 2 plus 3x, and that is the first derivative. So here we need to confirm that this first derivative according to the formula is true. We have been given the function y equals ln of 2 plus 3x, so we need to differentiate it to confirm that the first derivative given by the formula is true. So dy dx should be d over dx of the argument of the log function, which is 2 plus 3x, divided by the argument itself, 2 plus 3x, and d over dx of 2 plus 3x, the derivative of 2 is 0 and the derivative of 3x is 3, so we have 3 all over 2 plus 3x, which actually confirms what the formula gave us for the case where n equals 1. So we can conclude that the formula is true for n equals 1. Now in the hypothesis step we have to assume true for n equals k. In that case we would have that d to the k of y all over dx to the k should be equal to, we simply replace every n in the formula by k, so we get negative 1 to the k plus 1 into k minus 1 factorial 3 to the k all over 2 plus 3x raised to the power k. Just like in any other proof by mathematical induction, this statement in the hypothesis step is going to be crucial in the proof of the inductive step, where we need to prove that the formula is true for n equals k plus 1. From here we have to move to the inductive step, where we need to prove that the formula is true for n equals k plus 1. So it will be important for us to recall the formula we are supposed to prove again. D to the n of y all over dx to the n equals negative 1 to the n plus 1 n minus 1 factorial 3 to the n all over 2 plus 3x to the n. So we are required in the inductive step to prove that d to the k plus 1y all over dx to the k plus 1. So I'm going to replace every n in the formula by k plus 1 in order to have an idea of what my proof in the inductive step would look like, so that it guides me so as to arrive and land safely. So in the inductive step I will need to show that d to the k plus 1y over dx to the k plus 1 should be equal to negative 1 to the n plus 1. Now n is k plus 1, so k plus 1 will give k plus 2 as the power of negative 1 into n minus 1 factorial. When n is k plus 1, I will get k plus 1 minus 1, which is simply k factorial, and then times 3 to the n being k plus 1 would have k plus 1 as the power, then divided by 2 plus 3x to the power n, and n in this case is k plus 1. So this is the statement that I will be seeking to prove in the inductive step. As was earlier mentioned, we need to make use of the formula obtained at the hypothesis step, where we assume that the formula is true for n equals k, in order to obtain the formula for the case where n equals k plus 1. Now, when you observe the statement that we have obtained from the hypothesis step, we notice that the order of the derivative is k. And since the next larger consecutive integer to k is k plus 1, it means that if we differentiate this formula with order k, we can now use to show that the formula will be true for n equals k plus 1. So symbolically then we can write that d to the k plus 1 all over dx to the k plus 1 would be obtained by differentiating with respect to x the formula for the case where the degree of the derivative is k. So this will be equal to d over dx of I'll write this statement in the form that we can easily differentiate with respect to x. So we'll get negative 1 to the k plus 1, k minus 1 factorial 3 to the k into 2 plus 3x to the negative k. This first part will remain unchanged. It is just the coefficient of the term in x there. Negative 1 to the k plus 1, k minus 1 factorial 3 to the k. So differentiating this part, the term in x there, we use the power rule. We then have negative k into 2 plus 3x to the power negative k minus 1 times the derivative of the bracket there, which is 3. In the next step, we have to be very strategic in arranging the previous statement in order to arrive the target statement that we are seeking to prove. Negative 1 to the k plus 1 into k minus 1 factorial 3 to the k dot negative 1 into k into 3 all over 2 plus 3x to the power k plus 1. In this statement here, the power of 2 plus 3x is negative k minus 1, which can also be written as negative into k plus 1. And so using laws of indices, we can then have that is equal to 1 all over 2 plus 3x to the k plus 1. And from here now, we observe the statement that we are seeking to prove. There is negative 1 to the k plus 1 times negative 1, and that gives negative 1 to the k plus 2 into k times k minus 1 factorial would just give you k factorial, while 3 to the k times 3 would give 3 to the k plus 1 all over 2 plus 3x to the power k plus 1. And from here we can observe that we have already had the proof of the formula for the case where n equals k plus 1. So we conclude that formula is true for n equals k plus 1 and is thus true for all n belonging to the set of positive integers by mathematical induction.